Now let's look at slightly more advanced case of integration where we have a sinusoid. So we have our axis and we have a signal that goes up, comes down, and then goes up again. So in this case the area is increasing here and the area is decreasing there. So the one thing about integration is it depends on where you are going to start the integration. So in this case let's assume that there was no signal before this, and this is sort of where we are starting our integration. So initially the area is 0, and as you can see it keeps increasing. So till about this point the area is actually increasing fairly fast because the slope is high, right? So the area is increasing fast, and then around here the area is slowing down, so it's sort of saturating out. So till here the area is still increasing but not as fast, so it's sort of slowing down. And then here it's starting to go negative, so it's starting to come down, and here this it sort of gets smoother when it comes down and probably goes to 0, because this area I've not drawn it well, but this area should be the same as that area. So this sort of is looking like a cosine wave, but the cosine wave doesn't cross 0, so it has the lowest value it has is 0. So basically it's sort of like if there is an amplitude of A, we are talking about something that looks like A minus cosine A into, not A actually, A by 2 into cosine something, which is at the same frequency. At least this component of frequency is the same as the frequency here. The two have the same frequency. So this much we can see, and we can also see that if you had a waveform that was at essentially half the frequency, so that means one period was like that, then it's quite likely that the area of this, even if the amplitudes were the same, let's say this was the original amplitude, let's call it A, here as well as here, then the amount of area that's under this curve is definitely more than the amount of area under this curve. So in this case, of course, the integration will depend on A, but it will also depend on the frequency, and it will depend inversely on the frequency. So it will go down as 1 over f. Of course, this is not surprising given that we know that because this is the integrated value, it's the opposite of differentiation. When we differentiate it, it goes as a linearly with frequency. I mean, it goes up with frequency. So when you go down from here to here, it should go down with frequency. So this is not surprising. So the amplitude of an integrated signal, basically of the area, is going to go down with frequency, and this is what we'll see in Python. So what we are looking at are the same inputs we've done before, and I'm created for 100 millisecond period 100,000 points. So 100,000 points, and each point will be 100 milliseconds divided by 100,000, which is a microsecond, which is this. So this is also being executed. So now if I go down, I'm taking a sine wave, and I'm taking a sine wave of frequency 10 Hertz, and because we have 100 milliseconds, 1 by 10 is 100 milliseconds, so you get one period of that. So if I look at a subplot of the sine wave, then this is what I get. I get the sine wave, and you have one period of the sine wave. So if I go back and I look at the integration, the cumulative, using the cumulative trapezoidal method. Uh, as I said in the last one, subplot is a way to split the plots because amplitudes could be significantly different. And so if I integrate this, I don't need that. I don't need that. So if I integrate it and plot it, uh, the one thing you would notice is that when you integrate it, you get 1 point less because you need at least 2 points to sort of get the area between them. So it always returns 1 point less than what you started, and this is one way of getting that information. Yeah, so this of course looks like a cosinusoid. I mean negative of a cosinusoid, but the minimum value that it's going to is 0. So again, looking at this picture, we can see that till this point, around this point, it looks like the slope is increasing here. The area is actually rapidly increasing, and then it starts to saturate out till about this point where the slope goes to 0. I mean, that's the slope and it's going through 0. And then the area starts to decrease. And initially the area starts to decrease rapidly, and then the area starts to slow down and not decrease as rapidly. And this is the area under the curve. So this whole area under the curve. So if this is 0, then the area we are talking about is this area, which is positive, and this area, which is negative. So at the end of an entire cycle, you had accumulated some area, but this entire area you lost out. Here's your 0 here. And this entire area that you had accumulated in one half of the cycle, you basically lost out in the other half of the cycle. So at the end of one period you gain nothing, and that's why the integral of a sine wave is 0 over one period. So the next thing I want to look at is what would happen if I had many periods. So I've just increased the points by 10, so I should have many more. I should have 10 more points. So if I looked at this, I should clear my plots. Yes, I have many more plots. So if I integrate it over many periods, I still see that the picture hasn't changed. Over every period, my integration is going to 0. Here's a clearer picture of the plot. So given that this is where we have a 0, this is half a period, this is a full period. So in a full period, if I looked at what I integrate, I get 0. And it doesn't matter how many periods I look at. And at the end of that, if I look at this period, 0.8, and I just go down 0.8, yep, 0. Is this interesting? Two reasons. One is if I take a basic trigonometric relation, cos of a plus b is cos a cos b minus sin a sin b, and put a is equal to b, I get cos 2a is cos square a minus sin square a. And I already know from Pythagoras theorem from before that if I have on a unit circle, if I had an angle a, then this is cos a and that's sin a. which is at a different frequency or has a different value inside here. So if I have A and this is not the same as this, I'll get it as some sort of a subtraction of cosines, and if I have sine and cos, I'll get it as some sort of a subtraction of sine, sinusoids. Irrespective of that, if I take the area of this, if I take the area of sine A into sine B, both these terms are going to go off to 0 on an average. And similarly, if I take sine with cos of A and B, it's very important to remember this is A and B, it's not the same expression. So as long as they are different, I'll always get 0. And this is the foundation of the Fourier series, that as long as you are not using exactly the same sine wave at the same frequency, you will always get an average.